We are going to continue looking at the probability of success for a logistic regression model here in this set of notes. But now we're going to focus on visualizing what this probability of success represents in terms of our model. So to help set the stage here, let's look at something that you would do in an introductory statistics course whenever you would estimate a normal linear regression model. What you would do is plot the data, meaning do a scatter plot. So you have X on your X-axis, Y on the Y-axis. The black dots that you see on this plot represent the actual observations in your sample. The red line on the plot represents then the estimated normal linear regression model. So you can see how that red line goes through the middle of those points. Now, whenever you would do a plot like this, you would look at, well, how close are these black points to the red line? The closer they are, the better the model fits your data. The better it's going to do in predicting your data. But then at times you might have an observation that falls way far from the line. In that particular case, you would say that particular observation is poorly fit. So now what we like to be able to do with logistic regression is do some type of plot like this. Unfortunately, though, it's a little bit more difficult. And the reason being is because our response variable is either 0 or 1. So in other words, if here's 0 and here's 1, we would have all our points relative to the y-axis at 0 or 1. And that wouldn't be very informative then to try to interpret how well the model fits the data in that particular kind of a case. So what we can do instead, that doesn't always work, but can work in many situations, is that how about we transform the data to a binomial format, similar to what we did before with the place-kicking data set, where we looked at the number of successes at each unique distance. We transform it to the binomial format, and on the y-axis, plot the observed proportion of successes for a particular value of your explanatory variable. That gives us sort of like a scatter plot, and then we can plot then the model on top of that to roughly make some kind of judgment about how well the model fits the data. Now note that this only works if, let's say, at each unique value of your explanatory variable, let's say we just have one explanatory variable only to make this simple. At each unique value of your explanatory variable, you have a sufficient number of trials for it. Because otherwise, if you just have, let's say, one trial at each unique x, well, then again, you're going to be plotting an observed proportion of successes of either 1 or 0. So you're back where you started off with if you were just plotting y itself. So if your x variable, let's say, is a continuous variable, this kind of plot is probably not going to be very helpful. Okay, so let's go back to the place-kicking data set. We're going to again look at the model that has distance as the only explanatory variable of interest in the model. And here's some code that we used before to transform the data from a Bernoulli response format, meaning that good was either 1 or 0, to a binomial format where we had W as the number of successes, essentially as our response variable. And so really briefly, we can use the aggregate function where we say I want to summarize good by distance. How do I want to summarize it? I want to sum up all the 1s and 0s at each unique distance. N here then gives us the number of trials at each unique distance, where I use the length function to essentially count the number of trials at each unique distance. And then I summarize it into a nice little data frame. So for example, at a distance of 18 yards, we had 2 successes out of 3 trials. My observed proportion of successes was about 0.67. So let's go ahead and plot then this data in a scatter plot-like format. So let me come over here to 10 to do this. So I've already ran this code here. Now to do the plot, on my x-axis, I want to pull out the distance corresponding to what's in W. Let me actually just show you what's in W here. So W Gives me all my distances and the number of successes at each distance in its good column. Then for my y-axis, I'm going to plot the observed number of successes at each unique distance. The n here for the good, let me just show you that. The n in the good column represents the number of trials for each unique distance. So by plotting W $good divided by N $good, I get the observed proportion of successes at each unique distance. Put a nice x-axis label, y-axis label. I'm going to put some grid lines on my plot as well. And so this is what I get. Let me get my plot. And so essentially what I have is a scatter plot of my data. The y-axis, I put estimated probability because it's like a observed probability of success. X-axis, I have the distance. And so we can see that we have a general trend here. As the distance increases, generally speaking, it seems like the observed probability of success goes down. So next what we can do then is plot our estimated logistic regression model on it so that we can better visualize this trend. So I can do that with the curve function. Now, in the past, we've actually plotted the logistic regression model before, and we use this kind of a set of code to do that, where we use the expr function to represent expression, and we put, we use the exp function to write out beta hat 0 plus beta hat 1 times distance divided by 1 plus the exponential function of beta hat 0 plus beta hat 1 times distance again, where we can't say distance itself. We need to say relative to our x-axis, so that's why we always put x there. Now we're going to actually use some simpler code to do this. We learned about the predict function already. This gives me my estimated probability of success, so I don't have to actually write out this full statement like this. So I can say predict object equal, my results are in mod.fit, new data, this is what x's do I want to predict at, or in other words, what distances. So I say new data, data.frame, distance equal x. So R sees this x there. And so what it's going to do is replace the x with 101 different values relative to the x-axis that I specify as 18 to 66 yards. So 101 equally distant values. Then continuing with predict, I say type equal response. And what that is going to tell R, as we've seen before, it gives me my pi hat. The color of the line is going to be red. And this is very important right here. Add equal true, meaning add this to the current plot that's being used. So if I do this, and then I take a look at then the corresponding results, there's my estimated logistic regression model plotted on what's like a scatter plot of my data. So let me come back over here to Word to actually see it. Okay. Now, here's a question. If I were to assess the fit of this logistic regression model, in other words, how well is it doing in predicting on my observed data? And if you were to assess this fit in the same way as you would with a normal linear regression model, like what we reviewed at the very beginning of these notes, what would you conclude? Well, let's come back here. We can see that we have some points that are far from that line. And if you use the same ideas about how to assess the model's fit as you with a normal linear regression model, you would say, oh, there are some cases that are poorly fit from the model. Unfortunately, though, you cannot, it's not that easy to make that kind of a judgment, okay? Because the reason being is because, remember, we have our initial data is a binary response. And so these particular points here and these particular points here represent there was only one trial. So my observed proportion of successes at each of those unique distances is either going to be 0 divided by 1 or 1 divided by 1. So this model would have no chance of resulting in a good fit if we use the same criteria as we would with a normal linear regression model. Even this point right here, 2 successes out of 3 trials. Well, again, think about the situation where you would have 3 trials. You can have 0 out of 3, 1 out of 3, 2 out of 3, or 3 out of 3. That's it. Only the 3 out of 3 would ever result in a point that would be close to that line. And so because of the binary nature of our data here, we have to be very careful with interpreting how far the points are from the line. What we need to do is to take into account the number of trials at each unique distance, and then use that to make a judgment about how good the model's fitting the data. Okay, so how can we do that? Well, what we can do is, instead of a scatter plot of the observed proportion of successes relative to the distance, we're going to do what's called a bubble plot. And all that a bubble plot is a scatter plot, but now the plotting point is going to be proportional in size to another variable of interest. For us, we want the plotting point to be proportional in size to the number of trials at each unique distance. So just to show you what ends up happening when we do this plot, and I'll talk about the code in a minute. This is now a bubble plot. Notice how these plotting points, these circles, are in different sizes. These sizes correspond to the number of trials at each unique distance. So for example, remember here I said there was just 1 trial for each of those points. There's 1 trial for just each of those points. So when I see something like that, then I realize, okay, I know that point is either 0 or 1 when we plot it relative to that y-axis. So because of that, I'm not actually even going to pay attention to this in order to judge how well my model fits the data. Even this point right here, that's a little bit larger of a circle relative to what we had here, but it's not very large at all. And so I'm not going to put much faith in judging whether or not the model fits good or bad for that particular plotted point, because I know there's very little number of trials at that. Now what I'm looking at is that some of these larger circles here, notice how those circles are relatively close to the estimated logistic regression model. And since they're larger circles, I know there's more observations that go into it. And so this makes me feel good about this model, that this model is fitting the data well. We'll continue talking about this shortly. But first, let's talk about how we get this plot. Okay. Oops. Rather than using the plot function, now we use a symbols function to do a bubble plot. Why do they call it symbols versus bubble? I think it's because you're very concerned about how big the plotting symbol is. So the syntax is exactly the same as what we saw with the plot function, but now I'm going to add 2 new arguments to it. Circles corresponds to what's this, essentially this third variable that you're plotting on there. And so if I wanted to, I could specify the number of trials as for circles. How big do I want the biggest circle to be? 0.5 inches. So let's see what happens when I do this. And so we get each of the plotting points is proportional to the number of trials. And we get something a little bit different than what I saw in the notes. Why? Well, if you remember, for a distance of 20 yards in the data set, there's 789 observations there, because these typically correspond to where point after touchdowns are attempted in terms of a distance. And this by far is the largest number of trials for any distance. I think the next largest number of trials is about 30. And so in the end, this unfortunately distorts the plot. So instead, what I did was I tried a few different mathematical transformations of the number of trials to see if I could get, let's say, the smallest value closest to the biggest value after that transformation in comparison to just using the number of trials alone. And what I ended up concluding is that a square root gives me a good look on the plot. And so that's what I did. And now we get the plot that we saw before, where it's not distorted by this very large circle too much. Now to plot then the estimated logistic regression model, I do exactly the same that we saw before, and here is now the plot that's in the notes. Okay, let me go back to the notes here. So generally speaking, if we look at these circles that tend to be large, they tend to be close to the line. This is a good sign. This is a good sign that our model is doing a good job. But there are still some points that might concern us a little bit. So for example, here at 51 yards, we see a relatively larger circle that is, in terms of the distance from the red line, is approximately, actually I think I have it in the notes. So the red line is at pi hat 0.49. The observed proportion of successes is instead 0.73. So we're off by about 0.24. So that concerns us a little bit to see that. And later in chapter 5, we will look at ways to formally assess how well a model fits the data, and we will come back to this as well. Another example was at 32 yards. Let's go back to the plot. So here's 32 yards, and we can see that this particular circle is a little bit far from the line. Obviously, this is kind of there's some judgment here in deciding, well, how close do I want these circles to the line? I think of this as an informal measure of how well the model fits the data here. It's something that you typically, if you can, always try to do. And then in chapter 5, we will look at some more formal measures of fit, and we will actually connect this informal to the formal so that you can better make sense of what's occurring here. Now let's say instead that our plot looks something like this, where we have now these two blue circles that were added to the plot. If I were to see something like this, I would be very, very concerned about my model, because this says that I have, at particular distances, I have some observations that are not being fit very well by the model. So even in an informal plot, informal measure of fit like this, I would say, okay, I'm really worried about my model. Now, another kind of plot that's often made in this kind of a situation when you have an introductory statistics course and you work with a normal linear regression model is a plot like this, where it's exactly kind of like what we saw before, except for now I have some green lines in the plot, and this corresponds to what are called confidence interval bands. So what that means is that if I were to, let's say, pick a particular x value, let's say right there, and I project up and then over, and then also keep on going and over, what this represents in a numerical sense is a confidence interval for the expected value of y. And so the reason why this is called bands is because we see how this confidence interval is banding around the red line there. And this is a nice plot to look at, because it says for every possible value of x that you're interested in, what's the corresponding confidence interval for the expected value of y. We can do something like that here in our logistic regression case as well. Now, to help do this, I decided to write my own function called ci.pi that automatically finds my confidence interval for pi, a walled confidence interval, that is. And so if you remember, there were some steps that we had to follow with the predict function and do some other functions involved with it to get our confidence interval for pi. This function essentially automatically does those steps for us. So especially for those of you who are taking my course, think about how this function here can simplify your lives, especially when you're taking tests or doing other graded parts of our class. You can use this function whenever you want to find a walled confidence interval for pi. Let's see how this function works then. So the function's called ci.pi. And one little side note, This function also helps demonstrate some of the great aspects of using R, how I can extend its capabilities to whatever I essentially want in terms of what maybe might simplify some calculations I like to repeatedly do. So ci.pi gets a function. I'm going to pass in 3 bits of information. First argument is new data, same meaning as what we had before with the predict function. mod.fit.obj, standing for object, my model fit object, resulting from GLM, and then alpha, so I can specify what my confidence interval is going to be, like 95%, I would put alpha 0.05. Then, exactly what we've seen before, I form an object called linear.pred that gets the results from predict. This is going to give me my estimated value of logit of, it's going to give me my estimated value of logit of pi. It's also going to give me the corresponding standard error. Then I find the lower limit of my interval for the logit of pi, my upper limit, and then I transform the lower and upper limit to be a lower and upper limit for pi itself with 2 lines of code. Lastly, I return in a list format that lower limit and that upper limit. So just to show you how this works, here's a test case. ci.pi. Let's say I want to do a confidence interval for pi when I have a distance of 20 yards. My model fit object is in mod.fit. I want a 95% interval. Look what R returns to me. I have a lower limit and I have an upper limit that are exactly the same as what we had before. Okay, so how can we now use this function to our advantage? Let me come back over here to 10. I can use this function now in my curve function to plot then for every possible value of distance from 18 to 66 yards. I can plot what that confidence interval would be, and then simply you can imagine 101 points on the plot relative to those confidence intervals. Draw a line between these points and then remove the points. So I say curve, my expression, ci.pi, corresponds to this function I just wrote. New data equal data.frame, distance equal x, because of how R works. Notice how when we use predict here, we use distance equal x there as well. Type equal, okay, sorry. So mod.fit.obj equal mod.fit, and then alpha equal 0.05. Okay, let me just actually run this once more in R so that we can see this with a particular distance. Let me make this a little bit bigger so we can see it all. Okay, so I have a lower limit and upper limit. In order for me to grab something out of the list, let's say like the lower bound, I can immediately say $lower there, and I get the lower bound. I can do exactly the same thing with the upper limit and immediately get that upper limit. And so that's what I take advantage here when I want to draw the lower confidence interval band. Let's say I want to make this band blue. I'm going to use a line type of dot dash. I could use a different line type if I wanted to. Add it to the current plot. Do these calculations from 18 to 66 yards. So if I execute that code, we will get then the lower limit for that confidence interval band. I can similarly do the same thing for the upper limit. Notice how I have an upper here. And just to show you, there's the upper limit. And then lastly, since I have two different colored lines, two different styled lines, let's actually put a legend. You should always put a legend on a plot in this kind of situation. The way I can do that is I can use a simple function called legend. I want to plot it relative to my x-axis at 20, so 20 yards. Y-axis 0.4, that's my estimated probability. I chose that location because there was nothing else on the plot in that location. And then there's an argument in legend called legend that says, okay, what words do you want us to put there for the legend? I'm going to combine together my logistic regression model and 95% confidence interval, CI. What line type do I want represented in that legend? Well, when I drew the logistic regression model, I use a solid line type. When I drew the confidence interval bands, I use a dot dash type. The logistic regression model was colored in red. The confidence interval bands are colored in blue. And so I use the COL argument for color for that. And then BTY stands for box type. Do you want a box around your legend? I don't think we need one, so I'm going to say box type equals N for no. And so when I run that code, then I come back over here, and there's my nice legend that helps describe what's being displayed in this plot. Okay. So for example, at a distance of 60 yards, what this says is that my lower bound for my confidence interval for pi should be approximately about 0.18, 0.19. For my upper bound, the confidence interval upper band should be approximately about 0.33. And so let's actually go back over here and do some of that calculation just to verify. So we just copy and paste some code that I'm using. So this is again at 60 yards. And yeah, so 0.18 to about 0.34. So that's what's nice about this plot, is that essentially it gives you all the values for all the confidence intervals for all the different values of x. Now you can do exactly the same kind of plot using a profile likelihood ratio interval. It is a little bit more complicated. My code to do this is actually in the course notes. So then that concludes in this subsection on doing some graphical displays of our probability success parameter corresponding to a logistic regression model.